The OSI model is a theoretical structure which forms the basis of communication for all network devices or hosts. If you look around you, network hosts are everywhere, from your iPad to your computer, baby monitor, your phone, or even your fridge freezer. And getting packets of data from one host to the next around the world is high priority. On top of that, with the advent of super high resolution video such as 4K, the need for network efficiency is greater than ever before. If we take this guy, for example, he wants to get the Facebook homepage on his phone, and as long as that happens quickly, he'll stay happy. But what actually happens when he presses the Go button on his browser application? Well, packets of data are created by the application, and the overall goal is to get those packets to their destination, usually on the other side of the world. This is done by adding headers to the outside of the packet, which contain sets of rules or protocols dictating how that packet must behave on its journey. Each layer of the OSI model contains its own set of rules, and depending on how the software guys wrote the application, how the engineers set the network up, and which hardware was used to do the job will ultimately determine how efficiently these packets will get to their destination.
Let's see what happens when we send the packet to the next host. In this case, a wireless access point.
By the time the packet gets to the bottom physical layer, it's collected all the information it needs to move on to the next host. In this case, the next host is a wireless access point, and the physical medium used to send the packet is radio frequency. An alternative physical medium to RF would be a copper or fibre optic cable, using electrical or light energy instead of radio. As the packet reaches the next host, it's the responsibility of that host to read the header information. Make a note of the information, repackage the header back up again, and send it on to the next host in line. This reading and storing of header data is absolutely vital in ensuring that the receiving packets can get back to the original host. The packet will move further up the OSI model, dependent on the host that's receiving it. For example, an unmanaged Layer 2 switch will read less header information than, say, a managed Layer 3 switch or a router. Not all devices have to read all 7 layers of information, as, amongst other reasons, this would lead to massive inefficiencies within the network.
Connectivity is an amazing thing. By now, we're all used to the instant connectivity that puts the world at our fingertips. From desktops or devices, we can purchase, post, pin, and pick anything, anywhere. We are connected to the world and each other like never before. But how does it happen? How does data get from here to there? How do different devices and applications connect with each other to allow us to place an order, make a reservation, or book a flight with just a few taps or clicks? The unsung hero of our connected world is the Application Programming Interface, or API. It's the engine under the hood and is behind the scenes that we take for granted, but it's what makes possible all the interactivity we've come to expect and rely upon. But exactly what is an API? It's a question everyone asks. Okay, not really, but we're glad you did. The textbook definition goes something like this. In computer programming, an application programming interface, API, is a set of routines, protocols, and tools for building software applications. An API expresses a software component in terms of its operations, inputs, outputs, and underlying types. Okay, to speak plainly, an API is the messenger that takes requests and tells a system what you want to do, and then returns the response back to you. To give you a familiar example, think of an API as a waiter in a restaurant. Imagine you're sitting at the table with a menu of choices to order from, and the kitchen is the part of the system which will prepare your order. What's missing is the critical link to communicate your order to the kitchen and deliver your food back to your table. That's where the waiter, or API, comes in. The waiter is the messenger that takes your request or order and tells the system, in this case the kitchen, what to do, and then delivers the response back to you, in this case food. Now that we've whetted your appetite, let's apply this to a real API example. You're probably familiar with the process of searching for airline flights online. Just like at a restaurant, you have a menu of options to choose from, a drop-down menu in this case. You choose a departure city and date, a return city and date, cabin class, and other variables. In order to book your flight, you interact with the airline's website to access the airline's database to see if any seats are available on those dates and what the cost might be based on certain variables. But what if you're not using the airline's website, which has direct access to the information? What if you are using an online travel service that aggregates information from many different airlines? The travel service interacts with the airline's API. The API is the interface that, like your helpful waiter, can be asked by that online travel service to get information from the airline system over the internet to book seats, choose meal preferences, or baggage options. It also then takes the airline's response to your request and delivers it right back to the online travel service, which then shows it to you. So now you can see that it's APIs that make it possible for us all to use travel sites. The same goes for all interactions between applications, data, and devices. They all have APIs that allow computers to operate them, and that's what ultimately creates connectivity. So whenever you think of an API, just think of it as your waiter running back and forth between applications, databases, and devices to deliver data and create the connectivity that puts the world at our fingertips.
To understand how an API helps with AV, we can make the analogy to a matrix-based HD distribution system. If the long-distance transmitters and receivers, or Balun pairs, are the SDVoE encoders and decoders, and the proprietary HD matrix is the layer 3 Ethernet switch, then the API would represent the front panel controls on the matrix switch. The API is what gives you the switches, buttons, levers and feedback about what you want the switch to do, but it's still the user, designer or programmer in control of what happens. Let's take a look at how a complex application is made simple by software built on the SDVoE API.
Welcome to the Inspection, Prevention and Suppression Bureau of the Excise Department of the Government of Thailand. My name is Thitikorn, and I am proud to be working for Vichai Trading 1983, and we were selected to be the system integrator of this state-of-the-art command center.
It's wonderful to see a company like Vichai Trading 1983 identify and deploy a video over IP network solution to provide an outcome such as this.
Vichai Trading 1983 approached us looking for a latest generation video over IP solution able to provide pixel-perfect video reproduction with no latency. It was our privilege to collaborate on the design and implementation using our Lightning product range. We were able to supply a fully configured video over IP solution which met all of the design requirements for this state-of-the-art project.
It employs video over IP technology in a unique environment requiring matrix switching, video processing, video wall, and video distance transmission. All technologies not normally associated with transport over standard networking infrastructure. A video over IP solution with Lightning incorporating the specific SDVoE technology allows all of that to be included in a single box solution. As CEO of IMAG Systems, it's great to partner up with Vichai Trading 1983 to produce projects such as this using unique technology from our Lightning product.